So we were discussing what is structural analysis. Though I wrote it as analysis, you have to understand that we are talking about not general term analysis. We are talking about structural analysis, and we were trying to define the tasks for the one who is going to do the analysis, structural analysis of various buildings, bridges, civil engineering structures, so on and so forth. So let us try to define this. So instead of giving you a definition like it is given in a book, what we are trying to do is we will try to understand it through a thought experiment. So for thought experiment, let us consider that this is a 1D skeletal element. It is supported by hinge support on one side, and let us say it is supported by roller support on the other, and this is subjected to, let us say, 10 kilonewton force here, then 20 kilonewton force here along the axis of the member, and let us say it is subjected to 10 kilonewton force here. Also, it is subjected to a, let us say, uniformly distributed load, and that is 20 kilonewton per meter. Now, we will start with applied mechanics. We will start putting things in the perspective as far as analysis is concerned. So let us start with the first task that we are often asked to do, and that is finding out reactions. Do you agree with me? Reactions. So the student whom I have asked to unmute should answer the question when I ask it. For example, now I have asked Swaraj to unmute. Swaraj, are you there? So there, if there is no response, I am going to put this student in waiting room. So Swaraj, are you there? No. So I am going to put him.
Yes, sir. Yes, sir.
Yes. So be attentive. Keep yourself unmuted because I need you to participate in the discussion. So now the first task that we are going to do is we are going to find out the reactions. That's what we have been taught in applied mechanics. Do you agree with me? Swaraj.
Yes, sir.
Okay. So how do you find out these reactions? Don't mute yourself and keep yourself unmuted. So how do you find out how do we find out the reactions? No. This is not going to work. So let me call Siddhant. Siddhant Banerjee. Can you unmute? Okay, I'm going to pause the recording. Yes. Now tell me, how do we draw? How do we find out reactions in this case? So we have to apply equations of equilibrium. Do you agree?
Yes. So first we do is summation fx equal to 0, then
Yes.
summation fy equal to 0. Then we take moment about any one point, and after
Yes.
finding that reaction of one point, then we substitute in summation fy or fx. Then we get
Correct. So, but even before doing all this, we need to draw the free body diagram. Do you agree?
yes, sir. Yes.
So to draw the free body diagram, what I am going to do is I am going to show two reactions here at hinge support. Hinge support can offer a vertical reaction VA, and it can offer a horizontal reaction that I am going to call it as HA, and it can also offer this roller support can offer only vertical reaction that I am going to call it as V. Are you with me?
Yes, sir.
Okay, so to this free body diagram, now I'm going to apply equations of equilibrium. So if I apply summation fx equal to 0, what do I get? Tell me. So it is 10 minus 20 plus 10. Do you agree?
Plus HA.
Plus HA. This must be equal to 0. So we get HA equal to 0. Happy?
Yes, sir.
So this is the first part. So HA turns out to be 0. Now, what is the next equation that we're going to apply? Summation of moments of all the forces about, let us say, point B equal to 0. So if I apply this equation, what do I get?
So
This is possible.
Summation upon Fy no sir first.
If you take summation Fy first, then you are going to end up with two unknowns, Va and Vb. So then it is difficult to solve for the two unknowns by having only one equation. So instead of that, if you take summation of moment about B equal to 0, the only unknowns involved are Va and tan. Are you with me?
Sir, we'll also need the distance between A and B.
Yeah, so that I will provide. So let us say this distance is 3 meters. So how do we write now? So 10 kilonewton, 20 kilonewton and 10 kilonewton, they are not going to produce any moment at B because they pass through B. However, Va is going to produce the moment, and that is Va into 3. And it is clockwise. Therefore, I assign negative sign. My sign convention is clockwise negative, anti-clockwise positive. Are you with me?
Yes, sir.
Okay. Current, you can mute in between, and during the reply, you can unmute because there is some background noise that is coming from the side. So whenever
Okay.
I ask the question, you can unmute. Yeah. So now let us take the moment of this 20 kilonewton. So this 20 kilonewton is acting on 3 meters. So we know that the total force is 20 into 3, that is 60. So I can replace this entire load by 60 kilonewton force acting at mid length, and mid length means 1.5, and this 60 kilonewton is going to produce anti-clockwise moment about B. So it is going to be 60 into 1.5. So plus 60 into 1.5. This must be equal to 0. So that gives me what? That gives me Va is equal to 60 into 1.5 by 3, that is 60 by 3, that is 30. And that was obvious because due to the symmetry of loading, Va as well as Vb is going to be equal to 30 kilonewton. If you apply summation Fy equal to 0, you will get Va as 30 kilonewton and Vb also as 30 kilonewton. Are you with me, Karan?
Yes, sir.
Okay. Now, so we have found out the reactions. So this part comes from mechanics. Happy? Karan?
Yes, sir.
And do we include it in analysis? Yes, we do include it in analysis. We have not yet defined what the analysis is, but let us try to understand what all is included in the term analysis. So this is a part of analysis. First part. Okay. Now, in mechanics, we never ask the question, why do you want to find out reactions? Reactions क्यों find out करना है? So there can be multiple reasons. We will answer, we will list out those reasons as to why we need to find out reactions little later. But before that, now let us come to strength of materials. So I will abbreviate it as SOM. So what is the first task that you do in strength of materials for such kind of member? So let me remind you few of the things that we have done in strength of materials, and we are going to connect everything together to see a global picture. So what are we going to do now? We are going to draw first level diagrams, and those are axial force diagram, shear force diagram, and bending moment diagram. Are you with me, Karan?
Yes, sir.
Okay. So how do I draw axial force diagram? So I already said that axial force can be either compressive in nature or it can be tensile in nature. And axial force is pair of forces. It is not a single force. This we have discussed already. What we are doing now is absolutely essential for design, because unless we have these diagrams, we cannot proceed for the design. So in this context, now I want to draw axial force diagram. So what am I going to do? So first of all, I am going to look at the loadings which are in the direction of axis of this 1D member. So if you look at this 20 kilonewton meter load, it is not in the direction of axis of the member. So it is not axial load. So I am going to disregard this rule. To draw axial force diagram, I am not going to consider this 20 kilonewton per meter load because it is transverse to the axis. It is not along the axis. Are you with me?
Yes, sir.
Okay. So what are the loads that are along the axis? So I'm going to consider HA, but it is 0. I'm going to consider this 10 kilonewton load. I'm going to consider this 20 kilonewton load, and I'm going to consider this 10 kilonewton load. ये तीन loads हम consider करने वाले हैं. VA, VB, and 20 kilonewton per meter being transverse to the axis, they will not be considered while drawing the axial force diagram. Happy?
Yes, sir.
Now, just on the top of this axial force diagram name, I am going to draw the sign convention. So what is our sign convention? If this is a cross section, or if this is a section that we are considering, a pair of equal and opposite forces which try to compress the cross sections adjacent to this section, we are going to treat it as compressive, and we are going to treat it as negative. Are you with me?
Yes, sir.
And if you have pair of equal and opposite forces which are trying to elongate or which are trying to enhance or increase the distance between two adjacent cross sections to this section, then we are going to consider it as tensile, and we are going to treat it as positive. Happy?
Yes, sir.
Some of you may feel this exercise elementary, but I must ensure that everybody is on one page before we start the actual design process of form work. So that's why we are just giving the glimpses of what we have done till now, and with the focus on definition of analysis. अभी ये हम define करने की कोशिश कर रहे हैं. So now, if I take section anywhere between A to C, on the left hand side of section you have only one force along the axis, and that is 10 kg. कहाँ पे भी आप section लो between A and C, I am going to have only one force in the axial direction on left hand side. The moment the section shifts to portion CB, on the left hand side of this section I start having two forces. One is 20 kilonewton towards left and 10 kilonewtons towards right. So therefore I am going to write down the equation of axial force in two sections, one in section AC and another in section CB. Are you with me?
Yes, sir.
So let us do the calculations here. So the calculations for axial force diagram, I am going to consider section at distance x, but that x will vary from 0 to 1.5. This is the midpoint. So at midpoint you are going to have this 20 kilonewton load. That's what is given. So this is 1.5 meter. This is also 1.5. So x running from 0 to 1.5, x belonging to 0 to 1.5. So section lies anywhere between 0 to 1.5. What is the algebraic sum of all the forces on left hand side which are in axial direction? Mind you, we are drawing axial force diagram. We are not going to consider transverse forces. We are going to consider only forces along the axis. So if I take section anywhere between A and C, what is the algebraic? That section is drawn in this fashion. What is the algebraic sum of all the forces on left hand side? It is 10 kilonewton towards right. It is but obvious for equilibrium, the sum of all the forces on right hand side has to be 10 kilonewton, but towards left. We will cross verify that. On right hand side, we have this 20 kilonewton force and this 10 kilonewton force. 20 kilonewton is towards left, 10 kilonewtons is towards right. Algebraic sum is 20 minus 10, that is 10 kilonewton towards left. Do you agree with me?
Yes, sir.
So what kind of force this is? Is it axial compression or is it axial tension? Bolo.
Axial compression.
Yes. So therefore we are going to treat it as negative. So for any section between 0 to 1.5, I am going to have axial force of 10 kilonewton compressive in nature. Now let us take section belonging to 1.5, section belonging to 1.5 to 3. So if I take any section between 1 point, so this is the section. If I take this section, what are the forces on left hand side of this section? On left hand side you have 10 kilonewton towards right and 20 kilonewton towards left. So what is the net sum? Net sum will be 10 kilonewton towards left. Do you agree with me?
Yes, sir.
10 kilonewton. Now, if I consider the section on right hand side, all the forces on right hand side in axial direction, there is only one force, 10 kilonewton, and that is towards right. So I'm going to show this as 10 kilonewton towards right. So when x lies or cross section is taken anywhere between x equal to 1.5 meter to 3 meter, what is the axial force that is prevailing? कितना है axial force? 10 kilonewton. क्या वो टेंसाइल है या कंप्रेसिव है? Tell me.
Axial tension.
Yes. So therefore it is tensile in nature and we are going to treat it as positive. तो यहाँ तक का प्रोसेस आप सब लोगों ने स्ट्रेंथ ऑफ मटेरियल्स में किया है. इसमें कोई रॉकेट साइंस नहीं है. आई एम नॉट टीचिंग ए न्यू थिंग. It's you already know this. Now we are going to plot axial force diagram. So how does this axial force diagram look like? So I'm going to mark all the important points. This is point B. This is point A. And this midspan is point C. Agreed? Are you with me?
Yes, sir.
Okay. Now, for section anywhere between 0 to 1.5, the actual force is 10 kilonewton. So I'm going to draw this as on negative side because it is compressive in nature, and I'm going to write the magnitude as 10 kilonewton. I can either write it as compressive or I will simply give negative sign with the understanding that compression is negative for me. So in portion AC, the axial force diagram looks like this, and in portion CB, the axial force is 10 kilonewton tensile. So there is an abrupt shift from compression to tension here. We will discuss about this abrupt shift little later, but this is plus 10 kilonewton. Do you agree with me? This is how the axial force diagram looks like.
Yes, sir.
Happy?
Yes, sir.
Now, just give me a second. Okay. Now, can you tell me, looking at this diagram, how can you define the axial force diagram? Axial force diagram मतलब क्या? अगर ऐसे पूछा जाए तो आपका जवाब क्या होगा? बोलो. Yes, Karan. Karan, are you there?
It is a diagram which is drawn using only the axial loads, uh, and the compression is considered to be negative, which is the downside, and hence.
So, just a second. So, to define axial force diagram, do we need to specify that compression is negative and tension is positive? No. So, instead of that, I am going to ask series of questions so that we define something called as axial force diagram, which is a first level diagram in strength of materials. I am going to ask few of the students. For example, let me ask Tushar, roll number 18, division A. Can you unmute Tushar? Roll number 18, division A, Tushar.
Yes, sir.
Yes. So I'm going to ask you a few questions. You will answer that. First of all, tell me, is this axial force diagram a graph? Is it a graph? Yes, Tushar.
Is there
Tushar,
a straight line?
pardon?
There a straight line parallel to x-axis?
No, no, no. I am asking the simple question. Is it a graph or is it not a graph? Yes or no? Binary answer. Tell me.
Yes, sir.
Yes. So first of all, we are trying to define axial force diagram. So this kind of diagram can be defined as a graph. That is the first point that we have to understand. Happy? Tushar?
Yes, sir.
Okay. Second question. If it is a graph, and let us say this is x-axis of the graph, and this is y-axis of the graph. So on x-axis, which is the quantity that we are plotting? Tell me. If it is a graph, what is its abscissa? What is that we are plotting on x-axis? Yes, Tushar. Bolo. Okay, I will ask someone else. Let me ask Harsh Jadhav, roll number 15. Can you unmute?
Yes, sir.
Yes. So, do you agree that it is a graph?
Yes, sir.
So, if it is a graph, what are we plotting on x-axis? Yes, Harsh. If you don't know the answer, you can say so. Then we will not waste time and we can proceed.
Sir, I don't know an answer
Okay.
because
So
I
let me
joined now.
ask.
Maybe
So let me
the
ask
load-
someone else. Parth, roll number 16, A division. Are you there?
Yes, sir.
Yes. So what are we plotting on x-axis?
Sir, I don't know, sir. Are those the forces?
No, on x-axis we are not plotting forces.
Oh, distance, sir.
Length.
Distance.
Yes, distance. Very good, Parth. So on x-axis, what we are trying to plot is position on the beam. Do you agree with me, Parth?
Yes, sir.
Okay, keep yourself unmuted for some time, Parth. We are going to
Okay,
go
sir.
ahead with this discussion. So you are now, all of you are now going to perform a thought experiment. In that thought experiment, uh, you can imagine yourself walking along the length of this beam from point A to point C to point B. And you will be always monitoring your position with reference to A as the origin. So that is what we are plotting on x-axis. So wherever you are standing, its distance of that point or position of that point with reference to A as a chosen origin is being plotted on x-axis. Do you agree with me, Parth?
Absolutely.
Yes. So if we are plotting position on x-axis, what are we plotting on y-axis?
So the forces acting on that point are the total
Absolutely
amount.
correct. So on y-axis, we are plotting the actual force at that position. Do you agree with me?
Yes, sir.
Actual force at that position. Great. So we can define now axial force diagram as a graph where we plot the position on the beam on abscissa as abscissa and axial force at that position as ordinate. Abscissa stands for x coordinate, ordinate stands for y coordinate. Are you with me?
Yes, sir.
Okay, so we have defined the axial force diagram. So यहाँ पे हमारा क्या चल रहा है? We are walking along the length of beam and we are plotting axial force diagram. Now, इसी तर्ज पे, इसी lines पे, can you tell me what must be shear force diagram? Tell me, what must be shear force diagram? Yes, Parth.
Sir, the same way, instead of actual forces, we only calculate the shear forces.
Excellent. So shear force diagram is a graph where we plot position on x-axis and we plot shear force at that position on y-axis. Do you agree with me?
Yes, sir.
And what is the sign convention for shear forces? Shear forces के लिए ये हमारा sign convention है. This pair of forces is treated as positive. Happy?
Yes, sir.
Okay. And now when you are talking about shear forces, which forces are you concerned about? Are you concerned about 10 kilonewton, 20 kilonewton and 10 kilonewton? Or are you concerned about VA, 20 kilonewton per meter and 30 kilonewton? Bolo?
Sir, the UDL and the normal reactions.
Absolutely. So this all has been done in strength of materials. Nothing much to think about it. We know how the shear force diagram for this looks like. It is rise by the reaction, that is 30 kilonewton, then fall uniformly, that means form linearly because the load is UDL, therefore shear force diagram will be linear. Fall linearly by amount 20 into 3, that is 60. So when you fall by 60, you are going to hit 0 at the midspan, and then you are going to have minus 30 here, rise by the reaction. VB, SFD closes, we are happy. These diagrams cannot be open, they need to close. So therefore 30 kilonewton, this 30 kilonewton, this is positive shear force, this is negative shear force. This is how the shear force diagram looks like. Do you agree with me, Parth?
Yes, sir.
Okay. Now, can you, on similar lines, can you define what is bending moment diagram?
Yes, sir. We only calculate the bending moment for A, C, and B, and then draw it accordingly.
We
Although
do not calculate
when
it only for A, C, and B. We calculate it at each and every X. Are you with me? And we plot it.
okay,
For calculation
okay,
purpose, you may say so that only at 3 places it
yeah,
is required. However, we will plot this BMD over the entire beam. So it is also a graph with position on x-axis and bending moment at that position on y-axis. Do you agree with me?
yes, sir.
And how much is this? Tell me. WL square by 8. We are all aware of this. This is sagging bending moment. Our sign convention is sagging bending moment positive. And this is WL square by 8. So that is 20 into 3 square by 8. Do you agree with me?
Yes, sir.
20 into 3 square by 8. So these are the things that we learned as first few units of the strength of materials, where we did plot axial force diagrams, shear force diagrams, bending moment diagrams, and there can also be a similar diagram which I call it as twisting moment diagram. So what will be twisting moment diagram? You plot position on x-axis and twisting moment at that position on y-axis. Do you agree?
Yes, sir.
Okay, so these are called as first level diagrams that you have learned in strength of materials. Do these diagrams come under the analysis? Yes. So right now we are trying to list down everything that comes under the analysis. So first level diagrams, that's what I will say. So what do I mean by first level diagrams? You are
Yes, sir.
changing the position and you are plotting some quantity at that position. Are you with me? So in diagrams में x axis पे हमेशा क्या रहेगा? Position रहेगा. Happy? Are you with me, Parth?
Yes, sir.
ओके और वाई एक्सिस पे क्या रहेगा? वाई एक्सिस पे या तो एक्सियल फोर्स रहेगा या फिर शियर
The
फोर्स रहेगा
respective
या फिर
forces.
बेंडिंग मोमेंट और ट्विस्टिंग मोमेंट एट दैट पोजीशन. हैप्पी?
So we can write like y-axis respective forces.
Yes. So therefore here we can have axial force, you can have shear force, you can have bending moment, or you can have twisting moment. So this entire thing that you have learned in song comes under only one category, and that is first level diagrams, where we plot something against the position of it. Now I am going to ask you even deeper question. Why the hell are you plotting these diagrams? What is the purpose? Yeah,
What
tell
is?
me. What is the purpose?
So to know the point of contraflexion and inflection?
Yeah, so that you are talking with reference to BMD. In general, I am asking the question, why do we draw the first level diagrams? What can be the purpose? I will come to point of contraflexion in a while. But before that, what can be the purpose? Can anyone tell me? Unmute yourself and let me know. What do you think is the purpose? To pass in SOM? Definitely not. There must be something more to it. क्यों draw कर रहा है ये diagrams? Okay, Pururaj, roll number 21, division A. Unmute. Yes. Why do you think do we draw these diagrams?
Don't know, sir.
I couldn't hear you. Can you be louder?
I don't know, sir. What?
You don't know. Okay. Rishikesh Pandit, roll number 29.
Mm.
Why
I
do we
don't
draw
know,
this?
sir.
Why do we draw this diagram? So current says it is graphical representation. That's all right. But why do we do it? Why do we draw? Okay. So let me ask Shashank Gaikwad, roll number 49, C division. Yes, Shashank. Shashank, you are not present because I don't see your microphone sign. So are you able to hear me? If you are, please message me on chat, or otherwise I am moving you to lobby. Okay. Prajwal Singh.
It's so that we can design the structures that way
Design the structures that way. Okay. So
according to the forces.
what information exactly from these axial force diagrams, shear force diagrams, and bending moment and twisting moment diagrams are you going to consider for design? What is that information?
Sir, means as we can see from the shear force diagram and that on the on the ends of the beam the shear force is more. So that way we have to
There you are. So
give
precisely. So perfect. So why do we draw these diagrams? To locate maximas and minimas of axial forces, shear forces, bending moments, and twisting moments. Do you agree with me? So who did answer? किसने बोला है आंसर? बोलो. Please unmute. Let me know your name. Am I audible? Okay, let me ask Siddhant Banerjee. Siddhant, can you unmute? Siddhant.
Yes, sir. Yes, sir.
Yeah. So why do so? Have you understood? We draw these diagrams to have maxima and minima of axial force diagram, axial force, shear force, bending moment, and twisting. Are you with me?
Yes, sir.
So not only are we not only we are interested in finding out the magnitudes and nature of maximas of axial force, shear force, bending moment, and shear force, but also we are interested in the locations where these maximas occur. Do you agree with me?
Yes, sir. Absolutely.
Somebody said there is a point of contraflexion. So yeah, point of contraflexion in a way says that the point about which bending moment reverses the sign and it has to pass through zero. So that is point of contraflexion. On either sides of that point, you are going to experience contrary flexures. So if you are designing a RCC beam, if you need to provide reinforcement on top on one side, on the other side of contraflexure, you will need to provide reinforcement at the bottom. Agreed?
Yes, sir.
Okay, so point of contraflexion, yes, it speaks something about the zero of bending moment, location where the bending moment becomes zero. Not only that, on either side of it, you have contrary flexures. That means if on left hand side you have sagging, on right hand side it is hogging. If you only have bending moment becoming zero, but the nature does not reverse about that point, we call that as uh, only a point of zero bending moment. We don't call it as point of contraflexion. So all these details are captured through these diagrams. So in a nutshell, we draw these diagrams to locate critical sections and magnitudes of critical actions. Do you agree with me? Siddhant, do you agree with me?
Yes, sir.
Yes. So let me list the purpose of this. So what is the purpose? Finding out maxima, minima, and wherever it becomes zero, what not. All these things.
The location of, like, the exact location on the span.
Yes. So we draw these diagrams to get the magnitude of maximum actions. सिर्फ magnitude ही नहीं, location as well. Happy?
Right.
Okay. Now, what next? Do we stop there? या इसके आगे भी कुछ किया था आपने strength of materials? Do you remember? सिद्धांत, इसके आगे क्या किया था? So now we will focus on one of the diagrams. हम दो diagrams पे focus करेंगे, not one. We will focus on shear force diagram and bending moment diagram. Now for time being, forget about axial force diagram. Same thing what I'm going to do with shear force diagram and bending moment diagram. I can do it for axial force diagram, but let us right now focus our attention on these two diagrams. Can you tell me what are the critical sections as far as shear and bending is considered for this beam? कौन से critical sections है? Yes, Siddharth, बताओ.
Sir, the two extremes, top and bottom.
Correct. So the cross section on the leftmost side and on the rightmost side of the beam. These two cross
Yes, sir.
sections are critical as far as shear force is concerned. Do you agree with
Yes,
me?
sir. Yes, sir.
I will
Absolutely.
denote them as A and B. And as far as bending moment is concerned, which cross section is critical?
Sir, the topmost point of the arch.
Don't call it that. No, tell me the position. Where is this bending moment? ये जो maximum bending moment दिख रहा है, ये कौन से cross section के यहाँ पे experience होगा beam पे? Is it at mid length cross section?
Yes, sir.
Okay, so which cross section is important? Cross section at C is important as far as the maxima of bending moment is concerned. Considered. Do you agree?
Yes, sir.
Okay, we are not talking about axial force diagram and twisting moment diagram right now. We are focusing our attention on shear force diagram and bending moment diagram. So we have identified three critical cross sections. ये तीनों जगह पे अगर मैं इस बीम का क्रॉस सेक्शन लूं तो वो तीनों जगह पे क्या रेक्टेंगुलर है? Do you agree with me?
Yes, sir. Cross section is rectangular.
Yeah. So if I were to draw the cross section at A, B, or C, I'm going to look at the same figure, which is
Yes,
rectangular
sir.
in nature. Do you agree with me? And
Yes.
dimensions are also same. Are you with me?
Yes, sir.
So let us call this as depth and this as B. So B cross D is the dimension of this cross section. So observe, देखो, I am going to define a new term that is called as prismatic. ये word सुना है आपने? सिद्धांत?
Yes, sir. I've heard of the term.
So what is the meaning of prismatic member? So whenever I call the member as prismatic, तो उसका मतलब ये नहीं होता कि वो प्रिज्म शेप का है. It has nothing to do with the prism. When I say the member is prismatic, that means
It is uniformly spread.
so all along its length, not only the shape but also the size of cross-sectional dimensions remain
Yes.
unaltered. Are you with me?
Yes, sir. It doesn't have a wedge.
Yes.
It
So
is
it doesn't have
uniform.
it doesn't have taper, and it doesn't even have the change in shape. So अगर rectangular cross section है तो rectangular ही रहेगा, और उसके dimensions 100 mm by 300 mm है तो 100 mm by 300 mm ही रहेंगे. अगर क्रॉस सेक्शन अमीबा शेप्ड है तो वो अमीबा शेप्ड ही रहेगा और सब डायमेंशंस वैसे के वैसे रहेंगे. So it is not necessary that it should have rectangular cross section. Whatever is the cross section, the shape and size, अगर पूरे लेंथ के along preserved रहता है तो हम उस मेंबर को बोलते हैं prismatic member. Happy?
Yes, sir.
Okay. So this is a prismatic beam. So irrespective of where you take the cross section, visually it is going to appear same. Agreed?
Yes, sir.
Okay, but we have to understand when I am talking about the cross section in context of shear force diagram, I would have taken it either at A or at B. Agreed?
Yes, sir.
And whenever I am talking about the bending moment diagram, I would have
It will
taken
be
it
at
at
C.
So even though the cross section looks same, the location where it has been taken is different. The molecules that you are considering are different. Are you with
Yes.
me?
Yes, sir.
Great. So having said that, now what do? Now we freeze our location. Let us continue with the thought experiment that we were doing. We were walking along the beam and we came to know from shear force diagram that the very first cross section A itself is critical. Now I stopped walking along the length of beam. Are you with me?
Yes, sir.
Now I will not move an inch along the length. Instead of that, now I started walking along the depth of the cross section. Are you with me?
Yes, sir.
And I started asking the question. Let us say you already know neutral axis, so I am going to toss this term without definition. Let us say this is
Yes.
the neutral axis, elastic
Yes.
neutral axis in bending. So I started walking along the depth of the member. Jesse, when I was walking along the length of the member, I chose A as a reference. Do you agree with me?
Yes.
वैसे when I start walking along the depth of the cross section, I consider molecule at the mid length of this neutral axis as my reference. Happy?
Yes, sir.
So let us say this is my reference. So whenever I was occupying this position, I was at distance plus b by 2. Do you agree with me?
Plus B by 2. D by
Yes.
2. Yeah. D by 2. Yes.
When I started walking along the depth, I reached the neutral axis. I considered myself at origin. Are you with me?
Yes, sir.
And when I started walking down, I
Minus D by 2.
and at the extreme face of the beam, I assumed that I was at the position minus d by 2. Happy?
Yes, sir. Yes.
Okay. And I started asking myself a question. Let us say I am at distance y from the neutral axis. Are you with me?
Yes, sir.
So there are n number of molecules lying at the same location,
Yes.
same depth. So I asked myself a question: how much is the shear stress that these molecules must be experiencing? Are you with me?
Yes, sir.
And I asked this question for all values of y, from minus d by 2 to plus d by 2. Happy?
Integration within limits.
हाँ, इंटीग्रेशन करने की जरूरत नहीं है. क्वेश्चन आई एम आस्किंग इज व्हाट इज द वैल्यू ऑफ shear stress experienced by the molecules at a particular level?
Yes, sir. From minus d by 2 to plus d by 2.
Minus d by 2 to plus. And I came up with a diagram which is called as SSD, shear stress distribution diagram. सुना है कि नहीं?
Yes, sir.
And how does SSD look like for a rectangular cross section? It looks something like this. You must be knowing. Are you with me?
Yes, sir.
And how do I calculate the value of shear stress at distance y from neutral axis? तो ये जो टाउ है यहाँ का shear stress, इसकी वैल्यू में कैलकुलेट करता हूँ by the equation say by. I will define each of these terms for completeness. What is S? S is the shear force at that location. So what is the value of S in this particular case? 30. Are you with me?
Yes, sir.
So S is shear force at that cross section. So it is either plus 30 or minus 30. Doesn't matter. Into 10 power 3 Newton. Happy?
Yes, sir.
What is Y? What is A? So if I am drawing the level at Y and neutral axis falls on this side, the remaining area opposite to neutral axis is Y. Is A. Are you with me?
Yes, sir.
So wherever I am calculating, when I am at Y equal to plus D by 2, at that time A is 0 because there is no area remaining. Do you agree with me?
Yes, sir.
When I am at Y equal to minus D by 2, at that time also A is 0 because A is the area on the opposite side of neutral axis. Happy?
Yes, sir. Yes.
तो y के जिस साइड में न्यूट्रल एक्सिस लाई कर रहा है उसके अपोजिट साइड में जो रिमेनिंग एरिया ऑफ द क्रॉस सेक्शन है बाय डेफिनेशन दैट इज ए. हैप्पी?
Yeah.
And SA y bar. What is this y bar? So this y bar is nothing but the distance of centroid of this shaded area. तो remaining जो area है उसके centroid का distance from the neutral axis is y bar. Happy?
Yes, sir.
You can imagine as y goes on changing, this y bar also goes on changing.
Yes, sir. Absolutely.
So SA y bar. What is B? B is the width of the cross section available at Y. Are you with me? For example, let us say you are dealing with the I section. Are you with me?
Yes, sir.
And neutral axis is here. And
Yes.
you want to calculate the shear stress at this level Y. So what will be B here? At Y, what is the width available? It is only width of flange. So it will be BF. Happy? The width of wave, I'm sorry, BW. Do you agree with me?
Yes, sir.
हाँ, तो जहां पे हम shear stress की वैल्यू कैलकुलेट कर रहे हैं वहां पे न्यूट्रल एक्सिस को पैरेलल लाइन मैंने अगर ड्रॉ किया तो क्रॉस सेक्शन का कितना विड्थ उस लाइन पे लाया होता है दैट इज दिस बी. हैप्पी?
Yes, sir. Exactly.
ओके. एंड व्हाट इज आई? आई इज
The moment of inertia.
or second moment of area. It is also called as second moment of area or moment of inertia. About which axis? About axis of bending.
About
Okay.
axis of bending. Yes.
So about this axis, about neutral axis जो भी आया रहेगा that is this. Now, so what do you observe? So I have said all this for completeness. I'm very well aware that some of you must have done it thoroughly in the strength of materials. लेकिन जो कोई लोग भूल गए हैं उनके लिए मैंने ये रिवाइज किया quickly. However, you need to, if you have forgotten, you need to go back and you need to study this. Happy?
Yes.
Okay. Having said that, now tell me how do I define this diagram? How do I define the shear stress distribution diagram? कैसे define करूँ इसको? This is called a second level diagram. तो हमारे first level के diagram हो गए. अब हम निकाल रहे हैं second level diagrams. Are you with me?
Yes, sir.
And what are these second level diagrams? We are drawing these second level diagrams typically at the critical locations identified from first level diagrams. Happy?
Yes, sir.
And in these diagrams, we are going to move along the depth of the cross section. We are not going to move an inch along the length. Are you with me?
Yes, sir. We move along the depth.
Depth. So therefore, if you were to look at A as the origin, you are going to be always at the same location. You are not going to move along the X. You are going to move along the Y. Happy?
Yes.
Okay. So how do I define this diagram? Tell me. So is it also a graph?
Which one, sir?
This shear stress distribution diagram. Is it also a
Yes, sir.
graph?
Yes, sir.
So I'm going to now define it in the same fashion as I defined this SFD, BMD and AF. It is graph. I acknowledge that it is graph. Happy?
Yes, sir.
The moment I say that it is graph, I must specify what is its x coordinate and what is its y coordinate. X coordinate is called as abscissa, y coordinate is called as ordinate. So what is its y coordinate? What do I plot on y axis? Tell me. What is plotted on y axis here?
Distance.
The distance from
Distance
neutral
from
axis.
neutral axis. So is it position? Yes. But is it position along the length? No, it is position along the depth. Do you agree?
Depth. Yes.
So this is also a graph where I plot position along the depth, considering neutral axis as the origin. Are you with me?
Yes, sir.
So we are plotting position along the depth. And what do we plot on x-axis? What is abscissa? क्या plot कर बोलो?
X remains constant, na?
तो कहाँ constant है? ये vary हो रहा है ना x-axis पे.
Sir, stress.
Somebody said x remains constant. Constant. I am not talking about this x. This is the position. These
Oh,
diagrams
yeah.
we have
Sorry,
drawn.
sorry. Yeah, sorry, sorry.
These diagrams we have already drawn. That's now forgotten story. That's done. Now we are talking about this diagram. In this diagram, along x-axis, what am I plotting? Yes, tell me. किसी ने तो बताया था, बोलो वो सही है.
Stress.
हाँ.
Stress.
Which stress? Shear stress.
Shear stress. Yeah.
Shear stress at that position along depth. Do you agree with me?
Yes, sir.
Shear stress at that position along the depth. जो हमने दो में डिफाइन किए, सेकंड पॉइंट में डिफाइन किए. एंड दिस ऑल इज ऑकरिंग एट fixed location with reference to A. Are you with me? Siddhant, are you with me?
Yes, sir.
Okay. So this is also a graph where we plot position along depth as ordinate and shear stress at that position along the depth as abscissa. Now, what must be then? Something called as bending stress distribution diagram. Bending stress distribution diagram. So when it comes to bending, I am drawing this cross section which has width B and depth D, but this cross section is taken where? Tell me. When it
Yes,
comes
sir.
to bending, where should I take this cross section? At C, isn't it?
Yes, sir.
So it is cross section at C. And now I change the narrative of my question. Instead of asking at level Y from neutral axis, how much is the shear stress? Instead of that, I started asking the question, how much is bending stress? Are you with me?
Yes, sir. Yes.
And what comes to our rescue? Bending formula comes to our rescue. You all know that this bending stress distribution diagram looks something like this. Under sagging, this is tensile stress and this is compressive stress. So this is sigma BC max. Are you with me?
Yes, sir.
What is B? B stands for bending. Sigma stands for stress normal to the cross section. C stands for bending compression. And max stands for it is the maximum value of stress anywhere in the cross section in compression. Happy?
Yes, sir.
And this is sigma BT max. I am asking the question, what is the value of this stress at distance y? So we have a formula. What is the formula? Sigma by y is equal to n by I. Happy?
Yes, sir.
So what is the stress at this level? Stress at y is equal to my by I. Happy?
Yes, sir.
What is m? M is bending moment at this cross section, which is 20 into 3 square by 8. Y is the location from neutral axis where we are finding out the bending stress. I is moment of inertia or second moment of area about neutral axis. Are you with me?
Yes, sir.
So what is this bending stress distribution diagram? बोलो ये bending stress distribution diagram क्या है? It is the plot of position along the depth on y-axis and bending stress at that position on x-axis. Do you agree with me?
Yes, sir.
Similarly, we can draw other diagrams. So corresponding to axial force, we will have something called as axial stress distribution diagram. And corresponding to twisting, we will again have shear stress distribution diagram because twisting generates shear. Are you with me?
Yes, sir.
So these are the second level diagrams. So what are second level diagrams? Tell me. On x-axis, we plot either axial stress, shear stress, bending stress, or shear stress due to torsion. Are you with me?
Yes, sir.
So on x-axis, we are going to plot stresses. In first level diagrams, we were plotting forces. In second level diagrams, we are plotting stresses.
Stresses. Yes.
Happy? And
Yes.
what is there on y-axis? On y-axis, we have position, but along the depth.
Position along the depth. Yes.
Yeah. Happy? Okay. Now, the last question in today's class, and then in tomorrow's class, we are going to have a master stroke. We will understand strength of materials at a glance. However, we would not have completed defining analysis. इसके आगे भी बहुत सारा हमने किया है, वो कल define करेंगे. But सबसे पहले मुझे बताओ, why do we plot this second level diagram? Why the hell? Why should we plot?
Sir, because like whenever we are analyzing stresses and forces, it's not just along the length of the span, it is along the depth as well.
Okay, but why should I plot this diagram? What is
Sir,
the
in order to know the location of the critical points along the depth, because the span
Yes, you
can
are.
fail, because the
Correct.
span can fail in that direction as well. If there is like for example, if we have two forces applying from like being applied from the top, right, and somehow it causes a compression where it starts to hog in the horizontal direction,
Right.
then we need to have an idea of where the point is located, where we need to fix.
Correct. So let me summarize what you have said in concise words. What we are doing is we are trying to find out maximas, minimas of shear and bending, shear and normal stresses. Do you agree with me?
Yes, sir.
So we have known the critical cross section in the first level diagrams. Now I am asking a question. In that critical cross section, which molecules are critical as far as normal or shear stresses are concerned? Are you with me?
Yes, sir.
तो देखो first level diagrams, we were moving along the length, we could freeze the critical plane. देखो beam is 3D in nature. In first level diagrams, we could freeze a plane which is critical. Do you agree with me?
Yes, sir.
After drawing the second level diagrams, we can now we start moving in that critical plane and we have freezed a line, or we have freezed the molecules which are experiencing critical values of normal and shear stresses. Do you agree with me?
Yes, sir.
Now see where it is heading to. In 3D geometry, we freeze a critical plane. From plane, we freeze a critical location. All molecules along that location are going to be critically stressed, either in normal stress or in shear stress. What next? What should I do next? So I will give you the trailer for tomorrow's class and we will stop. So now I know that this molecule is critical. I will now start looking at various directions passing through that molecule, isn't it?
Yes, sir.
And I will freeze a direction which is critical. तो अब क्या करने वाले हैं? पहले क्या किया? Length के along position fix किया and we reached to a critical plane. Then we started moving along the plane. We freezed a critical level of molecules. Now we are not even moving an inch along the depth. उसी molecule पे हम डेरा देके बैठेंगे. But we will look at all directions passing through that molecule. Are you with me?
Yes, sir.
So this is the next level analysis, that is the master stroke of strength of materials, which is called as principal planes and principal stresses. We will discuss that in tomorrow's class, and then we will discuss what else also comes under the analysis, and then we will try to arrive at the consensus about the contemporary definition of analysis. Happy?
Yes, sir.
Okay, so with this, we are going to stop now. You already have the attendance link. You have to fill your attendance within next 5 minutes. If anyone has any doubt, you can ask me now. After each lecture, जैसे ही recording available होता है, I upload it on my YouTube channel, जिसका playlist का link मैंने आपके group पे already डाल दिया है.
आप शेयर कर रहे हो अटेंडेंस का लिंक?
कल ही किया.
वो तो कल भर दिया था.
वही that link that link
Same link
itself
is
you have
only
to use
active.
yes, every day you have to use that link. And I will consider attendance only during the period when I say that you have to mark the attendance. So therefore, Abhi, your time will start now. In next 10 minutes, you can fill your attendance. किसी को अगर कुछ डाउट है तो मुझे पूछो, otherwise we will stop the class.